Let us learn about exponential and logarithmic function. Let's draw the graph of y is equal to f1x is equal to x, y is equal to f2y is equal to x square, and y is equal to f3y is equal to x cube. On replacing the value of x by 0 or 1, we get the same coordinate for all given functions in case of y is equal to f1x is equal to x. On putting the value of x is equal to 2 for y is equal to x, we have y is equal to 2. Now we consider the function y is equal to f2x is equal to x square. On putting the value of x is equal to 1.5 for y is equal to x square, we get y is equal to 2.3. Now we take y is equal to f3y is equal to x cube. On putting the value x is equal to 1.2 for y is equal to x cube, we have y is equal to 1.8. Observe that the curves get steeper as the power of x increases. Steeper the curve, faster is the rate of growth. What this means is that for a fixed increment in the value of x greater than 1, the increment in the value of y is equal to f(x) increases as n increases for n is equal to 1, 2, 3. It is conceivable that such a statement is true for all positive values of n where f(x) is equal to xn. Essentially, this means that the graph of y is equal to fx leans more towards the y-axis as n increases. The growth of polynomial functions is dependent on the degree of the polynomial function. Higher the degree, greater is the growth. Is there a function which grows faster than any polynomial function? The answer is in affirmative, and an example of such a function is y is equal to fx, which equals 10 to the power x. Let's draw the graph of y is equal to fx is equal to 10 to the power x. For x is equal to minus 1, we have y is equal to 0.1. For x is equal to 0, we have y is equal to 1. Similarly, for x is equal to 1, we have y is equal to 10. This function f grows faster than f(x) is equal to x to the power n for any positive integer n. Definition 3. The exponential function with positive base b greater than 1 is the function y is equal to fx is equal to b to the power x. In this graph, we are looking y is equal to 10 to the power x. It is advised that the reader plots this graph for particular values of b like 2, 3 and 4. Exponential function with base 10 is called the common exponential function. We observed that the sum of series 1 plus 1 by 1 factorial plus 1 by 2 factorial and so on is a number between 2 and 3 and is denoted by e to the power x. Y is equal to e to the power x is called natural exponential function. Definition 4. Let b greater than 1 be a real number. Then we say logarithm of a to base b is x if b to the power x is equal to a. Logarithm of a to base b is denoted by log of a to the base b. If b to the power x is equal to a, then on taking logarithm on both sides, we have log of a to the base b equals x. We know that 2 to the power 3 is equal to 8. In terms of logarithms, we can write it as log of 8 to the base 2 equals 3. On a slightly more mature note, fixing a base b greater than 1, we may look at logarithm as a function from positive real numbers to all real numbers. This function is called the logarithmic function, is defined by log of x to the base b is defined from r plus to r. If b to the power y is equal to x, then log of x to the base b equals y. If b is equal to e, then we say it is a natural logarithm. Often, natural logarithm is denoted by ln. The graph gives the plots of logarithmic functions to the base 2, e and 10. There is a standard change of base rule to obtain log of p to the base a in terms of log of p to the base p. Let log of p to the base a equals alpha, log of p to the base b equals beta, and log of a to the base b equals gamma. We know that a to the power alpha equals p, b to the power beta equals p, and b to the power gamma is equal to a. Substituting the third equation in the first one, we have b to the power gamma to the power alpha is equal to p. This implies b to the power gamma to the power alpha is equal to p. Using this in the second equation, we get b to the power beta equals b to the power gamma alpha, which implies beta is equal to gamma into alpha. This implies alpha is equal to gamma by p. This implies log of p to the base a equals log of p to the base b divided by log of a to the base b. Another interesting property of the log function is its effect on products. Let log of pq to the base b equals alpha, log of p to the base b equals beta, and log of q to the base b equals gamma. Then we know that b to the power alpha is equal to pq, and b to the power beta is equal to p, and b to the power gamma is equal to q. But then a to the power alpha equals b to the power beta plus gamma, which implies alpha is equal to beta plus gamma. That is, log of pq to the base b equals log of p to the base b plus log of q to the base b. A particularly interesting and important consequence of this is when p is equal to q. In this case, the above may be written as log of p square to the base b equals log of p to the base b plus log of p to the base b, which equals log of p to the base b. And generalization of this for any positive integer n is log of p to the power n to the base b equals n into log of p to the base b. Theorem 5. The derivative of e to the power x with respect to x is e to the power x. That is, d by dx of e to the power x is equal to e to the power x. The derivative of log of x with respect to x is 1 by x. That is, d by dx of log x is equal to 1 by x. Let us have an example. Differentiate the following with respect to x. E to the power minus x. Let us have the solution. Let y is equal to e to the power minus x. Using the chain rule, we have dy by dx is equal to e to the power minus x into d by dx of minus x. Or dy by dx is equal to minus of e to the power minus x. Hence, d by dx of e to the power minus x equals minus of e to the power minus x.